Hi guys, so in this video I want to discuss about quantum computation. So first question which comes into our mind when we are discussing about quantum computing is that why we need quantum computing in the first place? Because right now we are doing all our operations in the class using classical computers. Why we need quantum computer in the first place? So this theory of quantum computation started when there was a failure in the Moore's law. So Moore's law, I guess you guys know. That means it is like the computer power will double for constant cost roughly every 2 years. That's what Moore proposed. But it was holding true from 1960 to some 2 decades. But it was not true now because when the computer size was reduced beyond a particular limit, the quantum effects started to get into picture, and these effects is actually causing the classical computers. That means we cannot reduce the size of the chip below one certain size. So because of this one, there is a limit to the classical computer. Okay. So the quantum computation is basically to use the quantum mechanical phenomena for the computation, and it is always faster than the classical computers. And some algorithms will give about exponential speed up when we compare with the classical computers. So this quantum computation, the concept was introduced by David Deutsch at 1985. So he was also thinking about the Moore's law, and he wanted to find an alternative to that problem. That means the classical computers, if this computation power um, cannot be increased beyond a certain limit. So he introduced the concept of quantum computation. And later, Peter Shor in 1995, he found out one algorithm using quantum computer. That means finding prime factors in an integer, of an integer, and also discrete logarithm problem. These two problems he solved with the quantum computer at a exponential speed up when compared to classical computers. Because these two problems are very hard problems in case of classical computers. That's with cryptography entirely is based on this RSA and all those things is based on this one, this finding prime factors of an integer. And also Grover proposed another algorithm, which is for searching through unstructured space. So that is also having some speed up in quantum computing. So basically, this was the motivation. That means failure of the Moore's law was the motivation that quantum computation was introduced. So next is actually let's see about the quantum bits which is used in quantum computers. Like in classical computers 0 and 1, we are using quantum bits in quantum computer. Quantum bit or qubit is analogous to bit. That means qubit can be in state 0 and 1. That you can see that notation given in 0 and 1 is actually Dirac notation. That okay. So difference between the classical bit is that the qubit can be in both states. That means that is the advantage of quantum computer. That means in classical bit we can be in 0 or 1, but a qubit can be in both states, 0 and 1. That means if we measure the qubit with qubit, we will get 0 with some probability, and in some other time if we measure it will be like 1 with some probability. So it is like a linear combination of states. You can see the representation in the second point. That means alpha 0 plus beta 1. So here alpha and beta are complex numbers representing the probability of occurrence of state. That means this alpha means if we measure 0, then if we measure, we will get 0 with the alpha square probability. And if we measure this particular state, we will get 1 with the beta square probability. But while measurement, we will get only one value, but that one value's probability will be alpha square and beta square. It could be 0 or 1, we don't know. So after measurement happens, the qubit uh, collapses to a specific state. That means qubit will collapse to either 0 or 1, even if it is superimposed states. So the reason was actually unknown for this phenomenon. So qubit is very real and can be represented in physical systems. Examples are like a polarization of photons. That means the photons polarization, depending on that one, we can represent as 0 and 1. And two states of electrons orbiting an atom. As you can see in the figure, this particular state can be 0 and the excited state can be 1. And like this, many more ways we can represent the qubit. So basically, the Bloch pair helps us to visualize the state of the qubit, because in classical computer, the Bloch pair doesn't make any sense because it can be only in 0 or 1. But here you can see the superimposed state. We can more represent more easily using the Bloch pair. So the Bloch pair we can obtain by substituting the alpha is equal to e raised to I delta cos theta by 2 and beta as this value. Cubic system can be represented by using the four parameters alpha 0 0, alpha 0 1, alpha 1 0, and alpha 1 1. So if we measure the first qubit and I get 0, that means it is like the first qubit is collapsed to the 0 state and the second qubit state is still in the superimposed state. So this basically the first qubit once that 1 0 and 1 1 is gone. That means the new state will be alpha 0 0 and alpha 0 1. That is the parameters for the new state. So this we can have a very simple observation here with the two qubits, I can have a superimposed state of four, like superimposed state of four states. So if I have three qubits, I can have a superimposed state of eight states. Likewise, if we think like that, for 100 qubits, we can have a superimposed state of 100 states. Not 100 states, 2 raised to 100 states. So, like that 500 qubit system, if we can have 2 raised to 500 states superimposed to as a one state. So, this is a very important property in case of quantum computing. So, this property we will use for our computational purposes. So, we can see that, but in case of classical computer, if I want to store a 500 bit number, I need one memory space. If I imagine like that, if I want to store all the numbers which can be represented by 500 bit, I need a very large memory space. So that limitation is not there in case of quantum computing because all this representations can be like in a one state as a superimposed state. This is a Bell state or EPR pair, which is a very important state. So here the thing is that there is no 0 1 or 1 0 state. So the advantage of this state is actually if you measure one qubit, the other state qubit is known without measurement. Means if I measure 0, the second qubit will be also 0. If I measure the first qubit as 1, the second qubit will be also at 1. So with one measurement, we can know the state of the second qubit also. So this is the slide for explaining about the single qubit quantum gates. Quantum gate not gates converts alpha 0 plus beta 1 to beta 0 plus alpha 1. The only constraint about this quantum gates matrix representation is actually the matrix should be unitary. So a unitary matrix is like a matrix whose inverse is equal to the conjugate transpose. I'm not getting into the mathematics of those unitary matrix that you can check online. So this is Hadamard gate is also another one important gate. Hadamard gate is also a single qubit operation. So it will convert zero qubit into, that means if a qubit of state zero into alpha zero plus beta one. That's qubit of state one into alpha zero minus beta one. So it could be, we can construct like Hadamard gate will convert convert one state to somewhere in the middle of the both states. That is what. So it is also very important gate. So another multiple qubit gates, if you want, the important multiple qubit gate is actually the CNOT gate. So CNOT gate is actually more similar to the XOR gate in case of classical computation. So here you can see that X is 0, Y is like the same value of Y will come out as output. But if X is 1, the Y value is getting inverted here. So this is also like one of the most important multiple qubit gates which is used in quantum computing. We will come across the different other gates also in the later part of the sessions. Thank you guys.